Hope everybody can hear me. Still people coming in. So yeah, I'm Julien Verlaguet. I built Hack a long time ago, but now I've been working on a new project for a few years now called Reflex. So Reflex is a new programming language. It's pretty different from Hack because Hack is basically a gradually typed or optionally typed, depending on how you look at it, dialect of PHP. And Reflex is pretty different in the sense that it is not related to PHP anymore, so it doesn't have any roots in PHP. But we've worked hard to make it compatible with Hack because we still have so much Hack code at Facebook that this was something important. But yeah, so it's a pretty cool project. The team is pretty big. It's a team of like 8-10 people, depending on how you count now, that's been working on this for a few years. And it's the first time we talk about this publicly. So I am very excited, and whatever feedback you have, good or bad, I want to hear it all now or after the talk. And feel free to interrupt me. All right, so what is it? Reflex is a reactive programming language. So reactive is a term that's very loaded. So it's used in many different contexts. So I want to clarify a little bit what I mean by that. What reactive means in this context is spreadsheet semantics. So you know when you're using Excel, you have a spreadsheet, and then you modify one of the cells, and the fact that you modify that propagates changes across the whole spreadsheet, right? And so that's what I mean by reactive in this context. Now imagine a full programming language that works that way. So you execute your code, that code has external dependencies, and whenever one of these dependencies changes, it's the job of the runtime and the compiler to update the state of the world. So you write logic that just produces the initial state, and then it's the job of the runtime to update things. So it's very much related to incremental computing, and because the term reactive is used in different contexts, I just wanted to clarify that. So what can you use that for? Actually, surprisingly, for quite a few things. And I listed a few ideas here, but there are other things. UI is the most obvious one because there's the library called React for JavaScript that has been widely successful. And the concept there was you have a model that describes the state of your mobile application. You write the rendering logic, and then it's the job of the framework to update the view when the model changes. Another example, which is less clear and less common, is privacy. So that's something we care a lot about at Facebook, but we start to see privacy use cases in more and more servers out there. So imagine you're building a website, that website has different kind of data, and you want to determine if one of your users can see a specific piece of data. Well, what tends to happen there is that you compute it once, and usually it doesn't change. So it would be really nice if you could store it somewhere and then only recompute that privacy when the part of the external dependencies has changed. And finally, think about a compiler. And I know that to some extent compilers they use separate compilation. They try to make the time to recompile pretty slow. But imagine a C or a C++ compiler all written in Reflex, and now on every single keystroke, it recompiles only what's necessary without you having to specify what. So all these use cases, they have something in common, and that's you want to use Reflex whenever it pays to reuse computation. And so that's what I'm going to get into. But first, why is that hard today? All right, so I just mentioned the compiler example. Let's say it was your job to build a C++ compiler that just recompiles at every single keystroke and does that very efficiently by just recomputing what's necessary. Well, step one, you would probably recompile everything because that's the easiest thing to do. And frankly, if you can get away with that, you should do that because that's the easiest to maintain. Well, now let's imagine the file grows, your header file gets bigger, there's more data, right? Well, the first thing that comes to mind is you will try to store intermediate values so that you can reuse them for the next run, right? And that is cache invalidation. And cache invalidation is hard. And what makes it especially hard in this case is that you are storing something in a cache that is a result of a computation. So when you're storing something in a cache that is directly backed by a DB, things are bad, but not that bad. When you write to the DB, you just have to remember to invalidate that cache. But now if you're storing something that is the result of a computation that can have dependencies to other caches, other values, and now if you add to the mix that this could be threaded, well, good luck in validating that. You're probably going to get that wrong. And so that's where Reflex comes handy. That's what it was built for. The idea behind Reflex is you write your logic without worrying about reactiveness. I'm a little bit lying here, but it's just to simplify. And the compile and the runtime is going to decide what to memorize within your application automatically for you, and then it will track dependencies for you too, which means that when something that you depended on changes, it will go in and validate those intermediate values. And I'll get to the specifics of that. What's important to understand is that to memorize something, so memorizing consists in, I think you're all familiar with the concept, but just for the sake of it, it's basically consists in saving the association of parameters to a certain return value. So you have a function, and you basically save what this function produced. Now, to make that efficient and to work, what we had to do was to make sure that the effects are trapped within that function. So there's one solution, which is to make everything immutable and purely functional. And then you can memorize all the things you like, and that's fine. That's not the route that we've taken with Reflex. With Reflex, we've developed a style and a programming language that encourages you to mutate things locally. And the type system proves that those mutations do not escape the scope of the function. Thanks to that, we can then aggressively memorize a lot of intermediate results within the course of a program. So why a programming language, and especially why a new programming languages, right? There are frameworks out there, and there are a bunch of things to do reactive programming today. RX comes to mind, functional reactive programming comes to mind. There are a lot of things to build reactive software. However, what we wanted to achieve with Reflex was, when you look at those solutions, what you end up doing is you're not writing a program that produces a value. You're writing a program that basically composes streams or continuations or whatever it is you do. You're not writing regular programming. You are using constructs that allow you to build plumb together streams or whatever it is you're plumbing together. And so we didn't want that. We didn't want programmers to think about that. We wanted them to just write regular code that doesn't know anything about reactiveness. Now, it's true that Reflex, in that sense, is strictly less expressive than RX, for example, because Reflex doesn't let you talk about previous values, right? However, it has a really nice side effect, so it's dumber than RX in effect, but a nice side effect comes to that, which is that the semantics of pull or push is the same. And for us running a big website, this is actually a very important property. Let me try to be more specific here what I mean by that. I write a program in Reflex, and I have a server that is pushing me updates, right? Whenever the database writes something, it recomputes that value and pushes me the update. If I work in production at Facebook, and for some reason I've decided that this data center or this region or this server cannot handle that load anymore, I can cut that connection at any time, restart it in another machine. As long as it's backed by the same DB, it will have the same semantics. And so that's something very valuable for a company at our scale. So what about the language itself? So as I said, basically three things to remember. One, it's not purely functional. It's a style where we're functional at the function boundaries. So whenever you call within a function, or whenever you return something from a function, we encourage you to pass around immutable values. But within the scope of the function, and we'll see how later, you can mutate things all you like. And it's guaranteed to be safe. OO and FP are merged, so that's probably, I see some people frowning here. And what I mean, I will show examples of what I mean concretely by that, but Let me explain in a nutshell. So, and this is a gross simplification, of course. Let's say there are OO languages on one hand and FP languages on the other. The basic block of an OO language is typically an object, and the basic block of a functional language is typically an ADT, to manipulate data, algebraic data types. And what Reflex does, it really merges the two. So you can use an object as a variant if you want, you can use an object as an object if you want, and you can really mix and match the two styles. And I'll show later how. Finally, and that's probably the key point of the language, reactivity is implicit in the sense that you will see no construction talking about streams, signals, events, whatever it is. All of that is implicitly dealt with by the runtime. So some more general features, and this is just a non-exhaustive list to show that the language is actually pretty rich. So it's statically typed, it has generics, it has type classes, it has all sorts of things that you would expect from a modern programming language. All right, let me show you what this language looks like. So, So this is a very, very simple example. I don't think it gets any simpler than that, but there are a couple of important things to note here. One, the syntax to introduce a variable. So here in this case, the y=1 is actually a let binding that is introducing a new variable. Two, the types within the body of the function are inferred, and they're not at the function boundaries. So here I had to write down the type int for the parameter and the return type. All the rest is inferred. And finally, it's an expression-based language. So in this case, you see that there's no return statement, and that's because we are composing value through expressions, if are not statements but expressions, etc., etc. This is the simplest possible example of a class. So one interesting thing to note is that the parameters of the class look like parameters passed to the name point instead of being in the body of the function. And when you think about it, it makes sense because if you want to pattern match on that class later, it makes sense to have these things syntactically close to each other. This class is immutable, and the function add1 is immutable as well, in the sense that it's producing a new point out of an old one. And that's really the style that we favor anyway. I'll show you mutable cases later. So that's the syntax for object creation, very simple. The important thing to note is that there's no new. And the other thing that is important is that this syntax creates an immutable object. So when I create point this way, I know for a fact just by looking at the expression here, without even looking at the definition of point, that this object cannot be mutated at this point. Just a side note is that there is actually a syntax to use named arguments, because as you can imagine, when you start having a lot of parameters, you may want to use them in different orders, etc. But that's just a side note. So now let's build something mutable. So one thing to clarify though, and that's probably the most important thing, the mutable on the X here doesn't mean that the field is always mutable. It means that when we use point in a mutable context, and I'll show later how that's introduced, that field can be mutated. Again, the same with moveX. MoveX is not a method that can be called in any context. MoveX, because it is declared mutable, is only accessible when point is in a mutable context. And I'll show later what that looks like. For now, you can ignore the exclamation mark in front of the X, and I'm going to explain later what that means. All right, so that's an example of a style that will encourage a lot in Reflex. I build a new point, and in this case, I said mutable points. And in this case, I'm saying, okay, I want a mutable version of that object. While it is in that version, it is safe for me to call all the mutable methods defined on it. And once I'm done working with it, if I decide to use the immutable version, I have to call freeze on it. So freeze does a logical copy. What that means is that in practice, it will often not copy because it can prove that object doesn't escape, the mutable version doesn't escape. But in the worst case, it might copy in some cases. And so that's a style that we actually favor. We're completely happy with you building a hash table, doing a lot of things with it, and then freezing it to pass it somewhere else. That's perfectly fine. And you can use, of course, persistent data structures if that's what you want as well. So what's the problem with that style, though? So for those of you who are familiar with functional programming, one of the things that can be a little bit heavy is when an immutable object comes in, and you need to massage it a little bit to do something else. So in this case, I've created a class triangle, and triangle has points in them, and I built a little function that wants to modify one of the fields, not modify, wants to build a new triangle where one of the fields deep in there has changed. And what you end up playing is you play with those boxes where it feels like you're digging out what you need to rebuild the new thing. So I've used the syntax with here. Don't read through the whole code, it's not very interesting, but basically what I'm trying to say is that this is pretty heavy to write. So Haskell has lenses to make that more comfortable, but we have something else, and I'll show why it's more suited for Reflex. So that's what we have. And I'll go through what the exclamation mark means through the several slides to come. But basically, the way to read this exclamation mark is when you put the exclamation mark in front of the T, you're saying, that's what I want to modify. So PT1 and X, the path is immutable, and what you want to modify here is the T. So it takes a little bit of time to get used to it, so I'll go through a couple of examples. So I took this data structure, very simple. There's a class C that has two fields, X and Y, and themselves have two fields that are integers. And I've represented what they look like in memory. So example number one, I'm on the wrong slide, sorry. Example number one, this is basically C-style assignment. So if you put the exclamation mark on the last field, what you're saying is that you want to modify deep. That's what C and C++ always does, okay? Now, if you write it this style, so what you're doing is you're saying, I want to modify field 2, but now field 1 is actually going to be a copy. It's a new value. So, are you following? Yes? Question over here? No? You're good? Okay, very good. Finally, the last one is this one, and that means that I want to build a new copy of my data structure, where the path to field 1 is now a new value, and the root, I want to replace it with a result. Okay? So when you think about it, another way to think about it is at one end, you are really using it as a lens in Haskell. That's this use case. At the other end, you're really using it like a C, C++ assignment, and anything in between is what the exclamation mark gives you that is pretty nice. So why is this nice? This is nice because it perfectly fits with the model. Immutable values come in. Sometimes there are mutable objects in there, and you want to mutate only the roots, but you still have to deal with a lot of immutability. And so that syntax comes in handy. Another thing to stress is that it's very rare to make mistakes on those because the types have to match. So if you try to put an exclamation mark on something that is not mutable, you'll get an error, and the other way around. So it's very rare that you try to put an exclamation mark on something and it actually works if it wasn't your intention, because otherwise the types wouldn't match. Finally, the exclamation mark is actually coupled to the let binding, because what will happen often is that we want part of a result to be to modify something, and the rest of the result to introduce new locals. So I've taken this example. Imagine a function that has an accumulator, and that accumulator comes in, and when it comes out, well, you typically want the new accumulator to replace the old one, but the result of that function, you want to give it a new name, and that's where mixing the exclamation mark with regular variables comes in handy. And that's why it's not a new operator. All right, so now let's go back to my reactivity code. So I've got my code. That's very simple code that does basically some filtering over some data that is fetching some data over a DB. And now let's say that something has changed here. Let's say that this thing changes. So one of the dependency has changed. Well, thanks to the fact that we have favored a style where everything that falls through a function call should be immutable, well, now what we'll be able to do is reuse db filter fetch this one. And hopefully that will propagate up this way, and by reusing all of these intermediate example values, we will be able to recompute very little. So for those of you who are interested, this is not a perfect model. We have a lot of tricks up our sleeves on how to make that better, but that's basically the basic idea. Another thing to stress is that you can't be completely naive on how you structure your code. If you pass around a big struct that contains a bunch of globals, it won't work. Finally, mutability can cross function boundaries by using annotations in the types. So it is discouraged, but it is not forbidden, because it would be too annoying for those who are writing APIs over mutable data structures. All right, so I said earlier that object-oriented programming and functional programming were merged in Reflex. What did I mean by that? So first, let me introduce the concept of a base class. I think all of you are familiar with it. Except that base classes are a little bit different in Reflex. So you can inherit from multiple base classes, but you cannot instantiate them. It comes with a bunch of really nice properties. I won't get into the details of it, but I will more explain how you can use them in a different context. So this is a very simple example. There should be absolutely nothing surprising here. This is a list of integers, and I have two classes that are implementing that list by extending int list. This is pretty much what you would write in Java modulo syntax. Now what's interesting is that you can write it this way too. And the two mean exactly the same thing. So this is really syntactical sugar for the slide that we've seen before. These two things are the same. So if you want to write in an OO style, you can. If you want to write in an FP style, you can. They both define the same thing. The same is true with methods. So I can go around all my classes and add, the method add1 to order them like you would in an OO language. Or I can use pattern matching directly in the base class. So I can write a function add1, and if you look at the body of this function, it doesn't start with a curly brace. It pattern matches directly. And that means when you write this syntax, you're saying, I want to add a method to the class nil this way. And you can also mix the two together. So you can say, I had a base class that was defining a method add1, and I decide later on to extend it with something in an OO style. So the two really are going to be stitched together and really mean the same thing. I took a more complex example here with generics. It's nothing to understand there. It's just to show you that we can write pretty expressive stuff in the language. As well, so it might be surprising that we are doing that, but you need a lot of those functional constructs to make the immutable style more palatable. Without these things, it would actually not be that nice to manipulate all of these immutable values. And that's why we decided to have that model where we're merging the two together. So I want to talk a little bit about the memory model, because it's a weird memory model. So it's a language that is safe in the sense that you don't have to write your malloc and free by hand, but it's not a tracing collector and it's not reference counted. So what is it? It's basically a model with two heaps, one minor heap and one shared heap. The minor heap is really just an arena that is leaking memory, and the shared heap is an MVCC. It works very much like a database, basically. But one property that it has that is extremely important is that whenever you store something in the shared heap, if that value was already there, then it's guaranteed to come back with the same address. So why is that important? It's important because earlier I said we were going to memorize a bunch of stuff. The problem when you memorize things is you first have to check that your arguments match something that you've seen before. And that can be very slow. And that's what this system is there to speed up. Because what we'll do with that system is we'll first take your value, put it to the shared heap, and then the shared heap will give back the same address if it's the same value. And now if you call repeatedly that function with the same object, well, it's one hash table lookup away to get that data back. So the other thing that's interesting is that thanks to the guarantees of the language, the minor collection is actually full. So, all right, I need to give a little bit of context on that. Typically, let's say you have a generational collector, and we're going to simplify things and say there are two generations, young and old. You have a young collector that is called several times, and what it does is that it collects 80% of the garbage, but it fails to see the whole garbage. And then you accumulate all the garbage that you eventually have to clean up with a full GC, right? The problem with that is GC pause time of the full GC, the major one. Because Reflex is built to build potentially latency critical things. And so for us, it's a big problem to have a GC that says, you know what, stop what you're doing, I collect memory. So what we did is we leveraged on the language, on the properties of the language to have a runtime that has a really interesting property, and that's the time to collect is big O of what you have allocated, and not big O of the size of the heap. The reason why that's important is that, yes, there's an overhead, but you can actually measure it. You can actually predict by how much this overhead is going to be. And in a nutshell, if you want to understand how and why, it's because when you have a minor collection, typically your problem are old pointers pointing to the new generation. And you try to keep track of that through write barriers or whatever it is, but that's the part that you have to approximate for your younger generation. And with Reflex, we have a guarantee that this doesn't happen, because the type system guarantees that it doesn't happen. So now when the minor collection finishes, well, the memory is clean. So we can collect with minor collections all the time like that and predict what the latency is going to be. All right, I'm on time. Wow, I spoke very fast. So future applications, there are a couple of things that we're interested in looking at, especially at Facebook. Easing the at-peak computation, that's actually a big problem at our scale. It's, imagine you have a lot of hardware and you want to compute at different times. Well, what you could do is compute in the morning, store those values, and then serve those values later on during the day. Another one, and that's pretty interesting, is whenever you need a remote cache. So imagine you have a small data center or a mobile phone or whatever it is. A mobile phone is a good example. You have a mobile phone, and typically what you want is to populate a local cache with data that lives on the server. And so when that data is backed by a database, that's relatively easy. But when that data is actually the result of a computation, you're actually struggling because you have to call back to the server all the time to tell you to ask, has anything changed? So if you write it in Reflex, in this case, what you could do is you write your logic server-side in Reflex, and Reflex pushes to your client whenever something has changed, which means that now for the app that is that is on your phone, they can consider all the local data as in sync, as if it was the live data that they just got from the server. And finally, and that's probably my favorite one, because we're actually doing this, it's the compiler itself. Remember I told you that example of my little compiler that recompiles every single time? Well, it wasn't completely innocent. The first version of Reflex was written in OCaml, and it was written in a subset of OCaml that transpiles pretty well to OCaml, to Reflex. And so we're not completely done porting the whole compiler and self-hosting the whole compiler, but we are like 75% of the way. And I'm pretty excited to look what this will look like when we plug it all together and we have our little reactive compiler that's out there. Finally, this is all super experimental in the sense that this is not in production yet. We're still trying to prove that it can work at the scale of Facebook. We want to apply this on very critical software at Facebook. And what I mean by critical is a lot of data, a lot of machines, a lot of code. But this is still very experimental. We haven't battle tested that technology yet. That's it. Thank you.
Okay, so we have time for a couple of questions. If you have questions, please come to the mic in the middle. Thanks.
Can you hear me? Hey, hi. Maybe you mentioned it, but I don't understand how you implement memorization. So do you insert a code sequence at the beginning of the function to check the value of the argument? Or?
Yeah, so, okay, maybe, then, and I had to remove a couple of slides about that, so that's probably why you didn't understand it. So before you get into the function call, the argument is interned. So if the interned means move to the shared heap. And that shared heap, by the way, is MVCC, which means that every single thread has a snapshot of the heap so that the database can carry on changing under your feet while you're serving traffic. Anyway, so you first intern the object. It's a full copy if it's the first time we've seen this object, and it will be relatively cheap if that object has changed little, right? Once it has been interned, you come back with an address, and that address is unique in the sense that if there was already an object out there that had the same value, it has the same address in the intern heap. So then what we can do is, for this function, look up that address. Did we already compute this? And if it did, it comes back with an address of another object that lives in the intern heap. So that's how it works.
Okay, so can I ask one more question?
Yeah.
So if you have like 100 of values, of different values, in a call to the same function, will you check for the 100 values, or?
So if you have 100 values, those values will first be interned, okay? If they come back with an address, it will be the same one as before, right?
Okay, so each time you just ask the heap if the object, okay.
So there's the intern heap, and there's a hash table that can associate to a function name and a value, comes back with a value if there's something. Yeah.
Okay, that was my question.
Yeah, sorry.
Thanks for a wonderful talk. A question for you. You said you have a self-hosted compiler. So, well, you plan to have one.
We're in the process, yeah.
Okay, so your compiler compiles to bytecode, to native code, or is it an interpreter, or is it what?
So there are 4 different backends, I think. So there's an interpreter, which is the thing that we use to bootstrap the self-hosting. There's, and that's the most, there's one that is the HHVM backend. And the reason we use that is because we need to interoperate with Hack, and that will ease this kind of interop. And finally, there's the native backend that targets LLVM. And that backend, that backend is the one that is really plugged into the reactive stuff. So all the other ones, they are just there to run once and for migration purposes. The real reactive stuff is a native backend that targets LLVM.
Okay, thank you.
You're welcome. Are you done? Oh, another one.
So, do you understand correctly that every time I call a function, it can return memoized result?
Yes.
But if there's a case when it's faster to compute results than to...
Yeah.
Do you deal somehow with this?
Well, so first of all, you have control over that if that's what you want. You get to annotate and say what you want to do. So there's a way to tell the compiler, shut up, that's what I want. But yes, the heuristics that you can build to basically establish what is worth reusing and what is worth recomputing is a never-ending game of optimization. So, yeah.
Thanks.
All right.
Okay, so if there are no more questions, like thank the speaker again.
Thank you.